So this next thing is called gravimetric analysis. And basically what it does is we start with two liquids, two solutions, and when we put them together, we get a solid. Okay, this is a precipitation reaction. Okay, and what we can do is then we can collect that solid and we can dry it, and then we can measure how much measure its mass on the balance, and that will tell us some information about how much of each component there was to start with. Okay, so I don't want you to focus too much on this idea of gravimetric analysis because it sounds like a big scary thing, but really it's just a precipitation reaction, which we've been doing for a while. Okay, so let's take a look at how we can put it into use, though. Okay, so we have our equation for the precipitation reaction, right? We have a couple of aqueous things coming together to have a solid precipitate. Okay, so it's a precipitation reaction just like any we've been dealing with. So let's take a look at the information in the question. So we are given a molarity. So that tells us that's going to be a conversion factor. And that's the molarity of the Na2CO3, right? And then we're given a mass for the magnesium carbonate, right? 0.5 grams of the magnesium carbonate, right? So I'm going to go from magnesium carbonate and I'm going to use that to find the sodium carbonate. Okay. And then I'm going to use the molarity as a conversion factor to find volume. Okay. So let's go through that process. Right. So first I have my given information. So I want to impress upon you this molarity. That's a conversion factor, not given information. Okay. Our given information is the 0.5 grams of magnesium carbonate. Okay. So we're going to start there. Mg CO3. Okay. And we're going to convert that to moles because I want to go from magnesium carbonate to sodium carbonate. I have to do that through moles. Okay. So first step is to use molar mass to get there. And it happens to be 84.32 grams of magnesium carbonate. Okay. So if I stopped here, my grams will cancel, and I would have an answer that is moles of magnesium carbonate. Now that I know moles of magnesium carbonate, I can do a mole ratio. So there's 1 mole of sodium carbonate for every 1 mole of magnesium carbonate. Right? So moles of magnesium carbonate will cancel, and if I stopped here, I would have moles of sodium carbonate. Okay? Now, remember our molarity of sodium carbonate, that's a 2CO3. That's the same thing as saying 0.1 moles of sodium carbonate per liter, right? So right now I have moles of sodium carbonate on top, and if this is a conversion factor, that means that I can flip it however I need. So I'm going to write a conversion factor that gets rid of the moles of sodium carbonate. So I'll put the moles on the bottom. My technology will stop arguing with me. And put the liters on the top. Okay, so I'm going to erase this bottom bit so that I can write the answer. All right, so my moles of sodium carbonate will go away. leaving me with an answer in liters. And we do that math, and we should end up with 3 sig figs, 0.0593 liters. Okay, but here's your stoichiometry. And then over here we use molar mass to get to moles, and over here on the right we use the molarity as a conversion factor to get out of moles. Okay. All right, last one. Okay. So when zinc metal reacts with hydrochloric acid, it produces zinc chloride and hydrogen gas, as shown in the equation below. What volume of 6 molar hydrochloric acid is necessary to produce 420.3 milliliters of gas at STP? Okay, let's take a look at the information in this problem. Okay, so remember, anytime you see that capital M, that's going to be a conversion factor. We're not going to start with that. Okay, that's going to be used somewhere in our problem, but not to start with. Okay, what we do have is we have a volume and we have a temperature and a pressure. Right? And it's a gas. Right? So PV equals nRT. And we've got the pressure, the volume, the temperature, and R is a constant. So that's going to get us to moles. Okay, so that's where we're going to start with this problem. So we need our milliliters in liters for our gas problem. Because the units of R are in liters. Right? And then the rest we have 1 atmosphere and 273 Kelvin. That's STP. Okay, so let's go ahead and rearrange PV equals nRT and solve for N. So the number of moles equals PV over RT. So the number of moles is equal to 1 atmosphere times our volume, 0.4203 liters, divided by the gas constant, liters, atmospheres over moles, Kelvin, times 273 K. Okay, and we're going to calculate that super fast. 206 times 273, and we have 0.24203 divided by the answer. So we should get 0.01863 moles of H2 gas. Okay. So that's a bit of a trek, but this is one of our paths to the mole bridge. Okay. So I'm going to bring that number down to the following slide because I've got more blank space down there, and then we can do the stoichiometry, okay? So we start 0.1863, and that should be, looks like 3 sig figs. So let's keep track right there. Moles of H2. Right, now I'm in moles, so I can go straight to moles of the other thing. So I'm going from moles of H2 to moles of HCl. Right, so there's 1 mole of H2 gas for every 2 moles of HCl. Right? So times 2. Right? So if I stopped here, I would have moles of HCl. But now we're going to use this conversion factor to get to a volume, okay? So I've got 6 moles of HCl per liter, okay? That's my 6 molar part, conversion factor part. Okay, so moles of HCl will cancel. Okay, so let me double check our answer, divided by 6. Right. So we should end up with, take this out of the way. So we should end up with 0.00621, which is slightly different than what the slides say, but pretty darn close. I'm close enough. Close enough for comfort. Okay. All right. So this, I believe this does it for us. It sure does. Okay, that's our last slide for this chapter, right? Please make sure to ask me questions, shoot me emails, join the office hours. I want to help, and this stuff gets a little complicated. So, but the biggest challenge, as usual, is interpreting these word problems. All right. So